Okay, welcome back, everyone, to our second of 3 workshops on building degree day decision support tools in R. This is our second session, and I'm pleased to be back with you. I'm Andy Lyons, and before we jump into our material today, a couple announcements. As I shared through the reminder email, given how much content there is to cover today, specifically working with weather APIs, I've made the call to not try to also talk about building Shiny apps today. So we've scheduled a part 3 of this workshop series in 2 weeks from today. And I apologize for kind of the last minute change, but that seemed pretty prudent. Shiny is also a big pond, and it takes a little getting used to working with reactive programming. And I do want to cover those principles of reactive programming and kind of build a Shiny app from that. So we'll do that 2 weeks from today. But today we're going to focus on working with weather data and weather data APIs. Before I jump in, was there any questions about stuff from last time that we'd like to? I will take a look at the homework that we did last time here in a second. Okay, well, we are a small group, so feel free to unmute yourself if questions do come up. And I've got my set of slides here, so we'll start off with a little review, and then we'll look at the homework, which is also a good way to look at the review. Okay, so what did we cover a week ago, right? So last week, we talked about what degree day models are, specifically accumulated degree day models, and that these are useful models that have been developed for decades because they do a pretty decent job at predicting the development of plants and animals, both of which are ectothermic, and therefore their metabolic rate, their development rate depends a lot on the ambient temperature. Right now, all other things, taken equal, things, like they have the nutrition and water requirements and all the rest of it. Certainly in managed systems like agriculture, we have tools to manage water and nutrition, but weather is the wild card. Nobody can control the weather, and that's why these models have been really good, and they're widely used for crop management and research. So planning when you're going to do certain time-sensitive crop operations. A lot of IPM falls into this category. Right? IPM techniques require good timing. But other things like when to adjust irrigation, when to adjust the nutrients requirements, all of that is based on timing. And we can do better than just simply saying we're going to do this on June 3rd, right? These degree day models give us better information than that. What these models do give us is this is important to know because it's not always obvious, right? Sometimes you have to read between the lines. But what exactly is being predicted? Is it a phenology event, such as when your pupa are going to become adults, or is it a continuous variable, such as the nut hardness, which varies continuously, right? So something that's going to be what is being predicted, when we should start counting, right? Because that's important, and that's how these models operate. That's called the biofix. Often, it's something you observe in your field. Other times, it's a calendar date. What version of the degree day equations to use? We know that there's about 6 different varieties, and they have upper thresholds and lower thresholds and different cutoff methods. So the models specify how to use, how to compute degree days. And then, of course, if it is a predicted event, when is that going to happen? When are we going to see that event occur in terms of degree days? And then the model can tell us what calendar date that's going to be, right? So in a high overview, that's what degree day models are all about. R is a good platform. You can do a lot worse than computing degree days in R because, unfortunately, working with degree days in any platform involves a lot of data wrangling. You got to get temperature data. You got to transform it in such a way that you can compute degree days. You may have to filter it. You may have to change the units, right? All that painful stuff. If you are working in the environment, our world, there is a package called Degree Day, which does the hard part of making those calculations. It doesn't do the data wrangling for you, but it'll do the rest. And as I mentioned last time, my group has developed a similar library of Degree Day equations for Python. So if you're a Python person, there's a library that you can use as well. The other thing we talked about last week was our goal here that we'll do in 2 weeks from today is to actually present a web-based decision support tool that presents these model results to somebody. And we have to come up with ways to present the results. One way you can do that is just in text. It's like, this Degree Day model predicts that the best time for you to till your soil is this date to that date, right? So we can present it in text and we can pull the text out programmatically. We can also present tables and, just kind of showing day by day how many degree days have accumulated. And conditional formatting simply shows like when the threshold is met, when the range is met. We can format that with code. But of course, plots are probably the best handy way to visualize the results of many models. And last week we looked at ggplots and making a static plot. 2 weeks from now, we'll look at interactive plots, which work in a web-based format. So broadly speaking, that's what we covered last time. And there was a homework assignment. And I know it was sent out a little bit short notice, but I did want to go through it real quickly because that's also a good way of reviewing what we covered last week, including some of the details. So the solution key is on the website right now, and I've got it opened here. So let's just quickly go through this homework assignment. So based on what we did last week, real similar. But essentially, I won't read through all of this, but we have another data set, right? So we have a CSV file of weather data from 2023, which is all cleaned up and ready to go. And what we're going to do with this historical weather data is kind of do a hindcast when we would predict, again, in 2023 at this location near Arbuckle, which is the closest Williams. I think that's north of Sacramento. When did the model predict navel orangeworm adults emerging? And this particular model that we're working with, which is pretty typical of pest phenology models, provides us the details. It says, if you want to predict the generation time for navel orange worms on almonds, right? So it's specific to that pair, that host pest system, that we should use the single sign method with a horizontal cutoff, with a lower threshold of 55 degrees Fahrenheit, an upper threshold of 94 degrees Fahrenheit. We should start counting at this biofix event, right? So this is an example of a biofix event, which isn't a calendar date. It's based on when a grower sees at least 75% of the egg traps that they've laid out, and there's a protocol for doing that. And they start to see an increase in the number of eggs that are, I think these are sticky paper traps, I'm actually not too sure. But when you start to see the presence of eggs increase on 2 consecutive dates, then that's your biofix. You take the first date as the date when you want to start counting. All right. So this is a pretty typical definition and operation for pest phenology, right? Where it's based on monitoring in the field. Okay. But once we know that date, we just look at what date is going to be 1,056 degree days after that. And that's when we predict that there will be the next generation, the adults flying around. And that would be an important time to be aware of, right? Because there might be things you can do to prevent them from mating, for example, pheromone disruption or other stuff. Okay, so that's the background. And we got some weather data for the homework assignment that you didn't have to import. Just you run this chunk of code right here, and it just kind of comes into your R environment. And you can see it's pretty standard daily minimum and maximum temperature weather data. It's been all cleaned up for you, but it's for the entire year of 2023. And we need to start this counting on what was April 22nd, or maybe April 23rd, if we want to start the counting the day after the biofix event, which is the suggestion. I don't know if it matters actually. And I don't know, I'd have to look at the paper to see if that's really specified. But anyway, so this is what the data looks like for this one weather station from 2023. So to get the date of the first flight, this will basically, this little piece of code right here will do that. So as you can see, you start with the weather data table that we just imported for the whole year. The very first thing you want to do, oops. The first thing we're going to do is we're going to pipe that into filter, right? Because we don't need all of these dates. We only need the dates starting from the biofix, right? So to filter a data frame based on a date column, this is how you do it. Simply use the filter function from dplyr. It is important though that the expression inside the filter function, because date, that is a date column. It's not a character column, it's a date column. So we have to say greater than the date we're looking for, but that has to be also a date object. So that's what as.date does. So now we have that date column, or now we have the filtered column, and now we compute the degree days, the daily degree days, using that single sign function from the degree day package, right? So we saw how to do that. And then also inside mutate, because really we don't care about the daily degree days, we care about the accumulated degree days. Also in the mutate function, we add another column for the cumulative sum of those, and that's what appears over here. So that's the table with the accumulated degree days. Now all we have to do is look up 1056, and that's what this little expression does here. Again, we're using filter, and then from there, you can use slice, you can use head, but basically we want to know the very first date when that accumulated threshold value has been surpassed, and that's going to be July 2nd. Okay.
Question?
Yes.
So what that mutate above does, basically you're telling it, okay, first I want you to add one column called DDF.
Yes.
And then I want you to add another column called ACCDDF based on that calculates something based on that DDF column that I just created.
Exactly. Exactly.
Okay. So mutate, you're telling mutate to add first one to add two columns, basically.
That's a very good point. Yes, we're basically we're using mutate to create two columns, and the values of the second column are derived from the first column. Now we could have split this, we could have totally split this out into two mutate statements. First, you create the daily degree days, and then pipe that into a second mutate function. But you make a really good observation that the mutate function does allow you to create multiple columns, and it does allow you to create, to fill those columns with the columns that are created earlier in the mutate function. If I had switched the order of this around, it would not have worked. But this works because we're first creating the daily degree day column, and then after that, we're using that in the cum sum function to create the cumulative ones. So
thank you.
Yeah, very observant there. Very that's a good detail. Okay, so that's how we get the first flight date, July 2nd. We're also told by the same model that the second generation of adults will appear after an additional 750 degree days, right? So we want to know, okay, well, when could we expect that? And to do that calculation, what I've done here is simply, again, using the table that has the accumulated degree days for the entire, from April 23rd for the rest of the year, and now looking for what is the first day when the accumulated value is 1056 plus 750s, whatever that comes out to, 1806 or something like that. Okay, so, and then take the first one of that gets August 6th by this method. Okay. Any questions, or did anyone do it a little bit differently and get same answers or different answers? Okay. All right, so whether or not you went through this, hopefully that's pretty clear, and that's kind of that's a good example of the wrangling that we did, and we will could do more of today.
So
Okay,
that slice min takes only the smallest value?
slice min.
Yeah.
Yeah, so slice min. So slice is a function from dplyr. These are all dplyr functions that will take the a row number as the argument. Slice min, the argument here is a column, and in the data frame or in the tibble, and slice min will return the entire row for the smallest value in that column, right? Which the smallest value of a date column is the first date. There's also slice max. If we had wanted the 5 earliest dates, there's other arguments you can throw in there.
Thank you.
Okay. All right, good. Okay, we're gonna get into more of these details. So if you enjoy getting your data wrangling fix, you should be pretty satisfied by the end of today. Okay, let's come back to today's topic, which is weather data, right? So finding the perfect weather data, I was trying to decide what is the right graphic to use here. I was thinking maybe needle in a haystack versus the unicorn. I went for the unicorn because needle in a haystack makes it seem like there actually is a perfect weather data source, and it's just difficult to find it. I don't think there's a perfect weather data source out there for these kinds of models. There's lots of trade-offs, as we will see. But some of the qualities of good weather data for decision support tools using the degree day models, location is a good one, right? Closer is good, and similar is good, right? So the ideal thing would be another weather station in your orchard or in your neighbor's orchard. That checks both of these boxes, but you may not have that, right? So you have to make some choices about what's the best location that represents the conditions at your location. Also need to think about, do you have the right sensors? We're talking temperature data, right? So everything measures temperature. Even we're working with some smart traps, smart sticky paper bug traps that have bundled temperature data, right? Sensors. And we're working with those in a different project. So that's not a big lift here, but other things you might do, you might need other sensors. And then is it maintained? We often forget about this. We see numbers, oh, okay, there's weather data numbers. But as farm advisors, as growers, as people who work in agriculture, will tell you if they know what stations are or are not maintained. Right, so that's important. It's not gonna tell you that probably through the API. Data is not very helpful if you don't have access to it. So ideally, the data is available quickly, right? Particularly if you're doing something like irrigation or something that trying to plan some operations. Hopefully the access to data is pretty reliable, pretty fast. There's not a lot of downtime. Sometimes you might have a dashboard where it allows you to download CSV files. So you might get access to the files. What I would say is better for the kind of thing we're talking here is there an API? And a lot of these weather platforms are smart, and they do have APIs out there. So that's becoming more common. Hopefully somebody has written an R package that makes it easy to work with the data in R using the API. You may or may not find that. And hopefully there's some metrics around quality assurance or quality control. All right.
Hey, let me make sure I'm on mute.
Okay. And then lastly, weather data, if it's a startup company and maybe it's really expensive, or maybe it's not going to be around in 2 years. You want to pick a source which is going to be sustainable for your
computer.
Okay.
Yes.
So we already went through this fact or fiction. I'm not going to go through these again. We talked about them at the end of last time. Basically, it depends, right? There is no unicorn of weather data, at least not that I've seen. I would love to have comments from people here if you have opinions about specific weather data sources, right? For degree day decision support tools, this is a little higher bar to meet because we're trying to make predictions. That's what these models are for. So that means we definitely need data from the recent past, at least since the biofix, and in this case, daily data. If what we're trying to predict hasn't occurred yet, then we also need future data, which is another higher bar to meet. So we all know from the Weather Channel that there's 7-day forecasts, and they're kind of reliable. But beyond 7 days, even the weather experts will say, we can't make good predictions beyond 7 to 10 days. But if you're trying to predict when your nuts are going to split, 4 months from now, then you do need some sort of weather data proxy for the rest of the season. All right. So 3 time periods, and we'll talk about how we can come up with data for each of these time periods. I mentioned this last week, but my group has put together a Google Sheet because we're learning this like a lot of people. I'm going to throw this link in here in the chat window. So if you know of a weather data source, feel free to chime in there. Feel free to sign up for office hours. We'd like to hear your thoughts about it. I can see some stuff has been added last time. I'm going to talk about 2 weather data sources, 2 weather data APIs, specifically for station data, because the first exercise we're about to do is going to be grabbing observed data from weather stations for the recent past. Okay. So CIMIS is a network of weather stations in California. There's roughly 150 of them. They're in the agricultural areas. This was initially a A&R project, I believe. What's kind of special or different about the CIMIS networks is that the stations are all on well-watered grass. So there's a book about how you set up a station, and they're usually sponsored by organizations or government partners. And you might wonder, well, why is it supposed to be on well-watered grass? Well, that's because we can use the data. If it's on well-watered grass, that's that's mowed as well. Then we can use the data that we get, temperature, humidity, solar radiation, I'm not sure what else, to model reference evapotranspiration, which can then be used to estimate the amount of water requirements for other things, not grass, but maybe celery or different kinds of other crops, right? So that's why that is there. This network is maintained by the Department of Water Resources, very big, very stable state agency. They provide access to the data through a web interface, which generally works well. You can get the CSV files through the web interface. The CSV files are also on an FTP server. You can request permission for that. They do have an API. The API is a little on the old side, but they are working on it this year. And I think by the end of this year, it should be much better. At least that's what we're hearing. So stay tuned if you've been frustrated with the instability of the CIMIS API. Hopefully it'll be more stable. And then there is an R package. There was somebody at Davis who created an R package. I don't know if this R package is still going to work after they finish their updates, but for now it's there. And a lot of people don't know that Spatial CIMIS is another product that's produced on a daily basis. And this is a interpolated surface of not all of the variables, but many of them. And you can grab those files via FTP, right? So here's the CIMIS stations. So what we're going to be doing is working with CIMIS station data because it's very popular. People like the stations. They're maintained by somebody. You can go look at them. But we're not going to use the CIMIS API because it's not terribly stable. We're going to use the Synoptic API. So the Synoptic is a newish, at least they're newish. Actually, they're not newish. They're well over 10 years old. They're new on my radar screen, but it's a company, and their business is aggregating weather station data from all over the country because, as you can imagine, this is not something most agencies want to deal with. So that's what Synoptic does. They get the data from dozens and hundreds of networks all over the country. They do some cleaning, they do some standardization, they put them on the API, and then they sell that to their customers. They are a public benefit corporation, so they have a pretty generous open access data program for non-commercial usage, which us as academics primarily is helpful. The API, I'm a fan of. It's very solid. It's quick. You do have to sign up to get a token, but it's well documented, and we're going to be using it. here in just a second. All right. And they do ingest CIMIS station data within a few hours. It's not instantaneous, but you can definitely get data from yesterday's CIMIS data. But before we start calling API resources, it behooves us to talk a little bit about the etiquette of using APIs, because these are data resources. They're being provided by somebody. They're not magical. I think a nice metaphor is to think of these as common pool resources, such as a pasture. We all benefit if we follow a few good practices so that this resource is available to everybody, right? Because yeah, there are limitations to bandwidth, there's limitations to computing power. So here are my top 10 practices calling APIs. Okay, number one, don't request data that you don't need, right? If you don't need solar radiation, don't ask for it, right? It's just more work on the server, it's more bandwidth, and you're just going to throw it away anyway, right? So that's one. Don't only get the weather variables you need. Don't request dates you don't need. If all you need are dates from like May through September, you don't need to get the whole year, right? So just, again, try to contain your request to just the data that you're actually going to need and not throw away. Number 8, some APIs provide a argument that you can use to do aggregation on the server, and that's usually going to be a better way. So for example, you might have hourly data, but all you need for your purpose is daily data. Look in the API documentation. Do they have a way to send you the daily data? Otherwise, you have to download a whole bunch of hourly data and then aggregate it yourself, which is not very efficient. It's not an efficient use of resources. They can do it faster than you could on the server and not have to send over a lot of extra stuff. Some APIs also do spatial aggregation. So you give it the name of a county and you get back one value for the entire county. It aggregates the data if it's a model surface. Number 7, break large requests into smaller pieces, right? If you need hourly data for 30 years, you're going to get a very grumpy API administrator if that's a single request, right? So break it into smaller pieces and learn the R techniques to do this properly. Almost all APIs have something called a user agent, which you can put into the header of your request. Some APIs require that. And this is, you can put anything in here. You can put in your phone number, you can put in your name, but put in something so that when the administrator of the API is looking at the logs, that they know who is using it. This is just good courtesy at a minimum, right? And if you know, if there's a problem with your request, you might get an email from the administrator rather than getting a you've been blocked message. We're going to do that here in our example. Don't request the same data multiple times. This is a big one, particularly when you're developing an application. You might repeat the same request over and over and over. That's just wasting bandwidth. So cache the responses to your request, and we're going to look at examples of how to do that. Number 4, throttle yourself if you're making large requests. Right, so throttle generally means putting a break in between your calls, right? So you have a lot of data, it's going to take 1,000 calls. Don't do them one after the other. Put in a little break between them. Another thing that you can do is schedule large requests off hours, right? So if you're going to be tying up the API, particularly if it's one that's free that you're not paying for, this is just common courtesy. It'll probably help you as well. If you do need a lot of data, then there's probably a better way than getting the API. Ask the administrator. Some platforms like CalAdapt allow you access to the source files, like gigantic, they're TIFFs and then netcdf files. So don't try to recreate the data through the API. I can promise you that's very inefficient. The API administrator of CalAdapt has relayed stories to me about postdocs or grad students who just really didn't take a class like this. And because of that, he blocked every IP address in Google Cloud, which caused me a lot of hits with some of my users. So be smart, work smarter, not harder. And then finally, all of this requires that you read the API documentation. All right, that's probably the number one thing. This will be a common theme today. Okay, and I invite other people to chime in about good practice work is seen with APIs.
Question,
Yes, Gary.
what's caching your request?
Oh, caching means saving a copy locally. Yeah, so the word cache, C-A-C-H-E, just means like a local copy, probably temporary. Right? You're not going to keep it forever, but at least keep it temporarily. And before you call the data, check to see if you've already called it by seeing if you've already cached it. Thank you. That's a good question. Okay, let's talk a little bit about some R methods for the code that we're about to do. First of all, many APIs require a token, a little bit like a password, not quite as sensitive as a password, but it is something that if somebody else gets, they could download data with your token, and there could be a cost to that, or it could bite into your quota. So you don't want your token to escape into the wild, which is more often done accidentally than by hackers. This is a bad idea, right? Putting your token in code. You can do that today, it's not a problem. But as a general practice, you wouldn't want this in your code because anyone who sees your code has your token, right? Related to that, if you do have your token somewhere in a file, might be a text file, might be something else, you don't want that to go into GitHub, right? Because once it's in GitHub, you can never get rid of it, or it's really hard to get rid of it, right? So if you are using a version control system, this is really important. Some better ways for reading your token into your code. One that's pretty easy to do and highly generally recommended is to read it in as an environment variable. So in R, somewhere on your hard drive, there's a file called .r-environ. It's just a text file you can open up with Notepad. Put a line in there that looks like this, right? Where you basically provide, you define a variable, an environment variable with a string, and that string is your key, your API token. And then if you do that, you restart R. If you can't find this file, there's a command that you can use from the use this package. It's called like edit R-environ. That will open it for you in RStudio, and then you can edit it right there. And then once you've done that, you can then read it through the sys.getEMD function, and then it's saved in a variable, and then you can use that variable in your API calls, right? Another approach is a little bit similar, where basically you save the API key in a text file, but you save it outside of your project folder. You save it somewhere else. Like I have a folder under my documents called my tokens, and I've got lots of text files there, and that's where I keep all of my tokens. And this is pretty safe as well, because that folder never gets backed up. Of course, this only works if it's on my laptop, if I'm running it locally. When we get to working with Shiny apps, we'll find another way that you have to, include your token. And then finally, if it's a very sensitive API token or something like a user account password that does have credit card attached to it, you can be more secure. Every operating system has a credential store, and then there's R packages like Keyring that allow you to save it there. So if your computer does get hacked by somebody, it's much more difficult to get it from your credential store. Finally, most API services have other options that you can set when you're creating your API, such as giving it just the absolute minimum number of permissions. With API tokens, there's not many permissions anyway. So, but for something like your Google credentials, you might create a service account, which only gives you access to one little piece of Google or one little piece of AWS. You can also set up IP filtering. Esri does this. You can set up expiration dates. You can put on usage limits and so on and so forth. So read the documentation from your API provider about what other security measures they offer. Okay, a couple more R methods that we are going to need to call APIs. One is we are going to have to work with dates. So dates and date times. So R is well provisioned for handling dates and date times, zip codes, durations, date time mathematics. The Lubridate package is from the Tidyverse, and this is a popular package. It's got lots and lots of convenience functions for working with dates. I'm gonna put this cheat sheet in the URL into the chat window there. I would recommend you take a look at it. And we're going to use a lot of functions from the Lubridate package today. Right? Here's some common ones, right? So a challenge often is that you get data maybe from a CSV file, or maybe it's from an API, but the date or the date time is provided as text. So you get something, you get any version of these, right? We all know this is a pain, that there's different ways that you can format dates, there's different ways you can format times. And you have to turn that into a date object or a date time object in R. So the Lubridate function has, what is that? 12 different functions that handle the most common order of the elements of a date or date time. So just kind of pick the one that matches your data. And then it does a pretty good job at figuring out, are these pieces separated by hyphens or dashes or spaces and so on and so forth, right? So these are convenience functions for converting text into dates. Here's an example of one, right? So a lot of times you get dates as text formatted like this, year, month, day, and then you can feed that into the YMD function, and that almost always gets it right. Here's an example of a date time character string. That T tells you that's time, and then you have to kind of figure out, is this 24 hours? Is this 12 hours? But the YMD HMS function from Lubridate does a nice job converting that into a valid date time object. Now, the default time zone is UTC, right? So that's Greenwich time. And this could be a local time zone. So when you are doing this conversion from text to dates, all of these functions I've listed above do have an optional argument called TZ that you can use to specify the time zone. All right, so here's the one for California, and we'll look at some more other valid time zone names shortly. Other times, you might want to create a date or date time object from scratch, or maybe using numbers. Sometimes, like the CMS API, you get the year column, the month column, the day column. You got to stick them together. And you can use make date time from Lubridate to provide the date pieces by numbers. And then there's also one called make date, where again, you provide the year, the month, and the day, and you get the date back. Right? So these are some handy functions from Lubridate. Let's talk a little bit about time zones, because this actually is a big deal with weather data APIs. Weather data has a timestamp, that's important. Particularly if you're working with hourly data. And when you tell it what time you want, you have to deal with the time zones. So you have to know how to specify time zones in R. And time zones do have standardized names. You probably have never told Buddy, that your time zone is America/Los Angeles. But for a computer, this and only this is the correct name for Pacific Coast time. It figures out the daylight savings time or not daylight savings time. That's handled automatically. Olsen names will show you all of the valid time zone names that you can use in these functions for the entire world. There's like about 600 of them, right? So pick one of these and you should be safe. If you do want to convert between UTC and Pacific time or European time, there is a function called with TZ, and this will return the date time in that time zone, not just assigning it that time zone, but actually changing the time value to that new time zone. All right, and we're gonna have to do this. Also, oftentimes we're working with dates. We want to pull out the month. We want to pull out the hour or the year. Again, for our analysis or for filtering, Lubridate has these functions: month, day, year, Y day. That returns the Julian date, right? So you can see for St. Patrick's Day, that's the month, sorry, the day, the month, the year, and the Julian day. Julian day means the day of the year starting like January 1 is 1, January 2 is 2, up to 365, right? So particularly when you're doing multi-year filtering or aggregation, these are helpful. Okay, I'll pause there. Any questions? I'm going through this kind of quickly. I don't expect you to remember this, but just kind of remember that there's this set of tools that you can use for working with dates.
So there is one time zone argument that tells the look, this data has this time zone, and then there's also another time zone function that tells a hey, I want you to convert it from the time zone that you currently have to this other one. Is that right?
Correct, yes. When you are making a date, whether you're converting it from text to a date time object, or you're creating it from scratch, it's important to specify the time zone, because the default is either going to be the time zone of your local computer, or it could be UTC.
If you don't tell it anything.
Yeah, if you don't tell it anything. So you'd have to read this. I think for the Lubridate functions, it defaults to UTC, which may or may not be what you want. Yeah, so you can't ignore, it's like working with spatial data. You can't ignore the projections, or you do it at your own peril. Working with date times, you should not ignore the time zone, because it could come back to bite you. Okay, let's talk about API request, because that's what we're about to do. What we're about to do is we're going to get station data from Synoptic, but unfortunately there is no Synoptic R package. So we're going to have to manually call the server and then parse the response. All right, so let's talk about how does this work in general. So in general, when you want to call data from an API, first of all, you have to create an API request. That's a little bit like an order form for data. Right? We'll talk about what are the pieces of an API request. All right, that's half the battle right there. Because then you send the request to the server does its magic, and hopefully it gives you back what you're expecting. Hopefully it gives it back you quickly, and you get a response. All right, so that response, it's like a box. It's not a data frame that you can immediately start working with. There's a bunch of things that come back and that are part of that response. And then you have to do some more manipulations to pull out the data from the response. So at a high level, these are the steps in working with APIs and making API requests. All right. Let's talk a little bit more about specifically that first piece, right? Because that's what we have to do next. So let's talk about that order form for making data. So the order form has different places. Just like, you're filling in an order form for something else, you've got a section for the bills or for your address, another section for what you're asking for. So to do this, you have to read the API documentation. We'll look at an example of API documentation here in a second. But these are the pieces of an API request. And this is pretty standard, whether you're using R or any other language or platform. Every API request has a URL. Like, this is internet stuff. So there is a URL that's going to be sent to. In addition to that, many API requests have, after the base URL, there's a path, right? It kind of looks like folder names, but there's another path. And oftentimes, this part of the URL are the different endpoints, right? So there's an endpoint for this case for time series data. There's another endpoint for station metadata. There's another endpoint for like the latency, right? So you have to read the documentation to find out what endpoints are available, and then what are the paths that you should use for the endpoint. Some APIs like CalAdapt, the path also specifies, it's also part of the query, right? With the parameters about how you're actually going to, what data you actually want to get. Then on top of that, you see the things with the question mark and the ampersand. Those are called query parameters. So they're tacked on to the URL. And this is where, like, what is the start date? What is the end date? What weather variables do you want? Right? So you get, that's where we'll see an example here down here in a second. The thing about the URL parameters is that the internet protocol only allows maybe 3,000 characters to a URL. So you can't put everything under the sun in your URL parameters. And most APIs, you don't need that much. But we'll see some examples of that. And you have to figure out how to, what are the parameters that the API recognizes and what values do they accept? So this is part of putting together the request. API requests also have a header. And the header is not part of the URL, but it's sent to the URL. And it contains things like, is there a specific format you would like the data back in? The big ones I've seen are JSON, CSV, and sometimes XML. Sometimes they want you to put in your token, that little password, as part of the header. Other times they want you to put it in as a URL parameter. And then there's a bunch of optional ones, like I was talking about the user agent field, that you would put that inside your header usually. And then finally, if you're requesting data involves a file that you have to send to them, like maybe a geometry, then you would put that in the body of the API request. We're not dealing with body today. We're doing relatively simple calls for a single location or single station, so we don't need that. Here's an example of an actual API request, which the token is fake, but everything else about this API request is real. And if I was to copy paste this into the browser, it would actually work. And you can see the pieces of it, right? So here's the base of the URL right there. And then after that, there's a little bit of a path. And then the question mark tells you, after the question mark, we start to see those parameters. So there's a parameter for the token, and it equals to that. There's a parameter for the station ID. There's a parameter for the vars. So the ampersands and converting, getting rid of the spaces, the package handles all that stuff for you. So it does a lot of those details. Okay, so let's talk about how do we do this in R. And the package that we're going to use, I really like it quite a bit. It's called HTTR2. And then these two packages we're going to use to parse the response. We'll come back to that later. So HTTR2, this is a great package that you can use to create an API request, and then to send it, and then to work with the response, right? To create a request object with the HTTR package, you're going to mix and match these functions like this, right? So where you basically pipe them together, each of these function, and there's some others, but each one adds a little piece to that order form, right? The base URL, the queries, the headers, and so on and so forth, right? So it's relatively easy. Here's an example of one that you could actually run it. So let's look at this example. So we are creating an API request object. We're not sending it yet. We're just creating it. So we start with the request function from HTTR2, and then the argument to that is going to be the base URL. Okay. And which we get from the API documentations. Then we can pipe that to the another function that will add in the user agent. Again, this is good courtesy. It's good practice. Brian Gailey is a colleague of mine, so I want him to know that I don't want to give him extra headaches. If there is a problem with my R package, I would like him to know about it, so he can give me an email. Request URL path append. In this particular API, this is partly how you specify what data you want back, is through these, through the path of the URL. Again, you have to read the documentation, but this piece here is a reference to a specific data set. This is modeled climate data. That's what I have to add to the path. And then this part, this function is where I specify those URL parameters. And again, I read in the documentation that there's a URL parameter called G, there's a URL parameter called start, and there's a URL parameter called end. And I can use these URL parameters to specify the year of data that I want. So again, this is future climate data, as well as the location. All right. So this expression right here gives me a nice little request object, and then I can look at that. And here's what it looks like. And I'm guessing this might work if I throw this in a browser. I actually haven't tried this. Let's see if that would work. Yeah, that would work. So if you, I'll throw this in the chat window here. If you want to, this is a baby request, so I don't think we're gonna like crash the Calvidad server. But that's basically a valid URL that is retrieving data dynamically through the internet. Okay, so right now, all we've done is created that request. So now we have to send it to the server. So there's a function called dry run. So we can pipe our API request object into dry run, and this will just kind of display what it's going to send when it contacts the server. And this all looks pretty good. When you're ready to send the request, then you feed it into request_perform. Okay, and that actually fetches the data, goes online. You might get a message from Windows that you have to let RStudio through your firewall. But this is now when it's actually fetching data. If it's quick, you'll get it back in less than a second. If it's not quick, it could take several seconds. If you've made a mistake, you might get an error message, right? But what this returns, what REQ performs, it returns a response object. All right, so now we have a response object, and we want to look at that response object. We've gotten it back. If you simply type the name of the response object, it tells you some properties of it. Looking for status 200, that's always a good sign. I look for that. That means it worked.
Question.
Yes.
So what you just did earlier, you copy pasted the super long URL, the HTTP-R2 gave you. You
Yes.
put it on a tab of your browser.
Yes.
And then you hit enter, and then the server spit out a lot of text data.
Yes. Yes. Yes.
Now, this thing that you're calling a response, basically will contain all that data. Do I understand correctly?
It contains this data plus some other stuff that we don't see in the browser.
Oh, okay. But that's the data you want to access, right? That's what you're asking from the server. Do I understand correctly? This is the game we're asking.
Yeah, exactly.
We're asking the server to give us some stuff that is contained in the response.
Yes, yes, exactly. So the heart of the response, the piece that we're interested in, is the data itself. We don't care how many milliseconds it took. We don't care how it sent back the encoding. We just want the data. So what you see in the browser is the body of the response by default. And this is a good way to test the URL. What we're getting here is JSON, right? So it's kind of hard to read, but easy for a computer to read. We could have asked it for a CSV file. There's another argument. We could have added another parameter. We could have asked to get a CSV file, and then it would be pretty close to being ready. We could copy paste it out of the browser into Excel and work with it from there. Okay.
Thank you.
Okay, so now we have that response back. The piece that we want is the body, right? But oftentimes you might want to look at the response first. So there is a function called response status that you can run if it equals 200. That means it worked. There's also a description that goes with that. If you want to look at all the other stuff that came back in that response, the stuff that we're probably not interested in, you can look at the headers of the response, and it tells you like how long it took. You can see all this other stuff. I don't even know what half of this is. Fortunately, don't have to worry about it. The date of the response. But the piece that we want is the body. So the body of the response is where the data is going to live. And we can pull that body out, assuming it's JSON, by piping it into response body JSON. And what that's going to do, it's going to take this structured but difficult to read information that comes down as text, and it's going to convert it to a list object in R. All right, so this is probably the most common way of extracting the data out of the body is as a list. Right. Again, if you asked it to give you a CSV, there are some other functions you can use if it's not JSON. All right. So now we have this object called, now we have a list object. Now it's in R, and we know how to handle list objects in R. This particular one, you can see this is a list with 3 elements. It has a name element. It has an index element. We're not looking at all the structure of the list, but that index element, that's where the dates live. Right? So this is, we asked for 30 years of annual data. So this is going to be the dates for those years. And then the data itself, that's going to be, in this case, TASMAX means that's the values, maximum average annual temperature, maximum daily temperature average over the year. Right? So you kind of have to know what that is. Now we have a list object, but that's not quite enough. What we probably want to get it is into a data frame. So this is a little bit tricky, or let's say it's very variable, right? So you need a set of tools to take that list object to pull out just the pieces that you need and to stick them in the data frame so then you can compute your degree days. So there's a few different ways to do this. This is a pretty typical construction where I tend to use, there's a variety of tools. We talked about Tiblify, there's pivot longer, sorry, there's unnest longer, unnest wider. There's a variety of packages that you can use to take this nested list and turn it into a data frame. And that could be a whole nother workshop, those techniques. But here's a construction that I frequently use is I create a tibble, and then, because I do have exact columns that I want to be in my data frame, some of those columns I'm defining manually based on the request. So not what came back from the server, but what I asked for. And then some of the columns, like this one here, I'm actually grabbing one of those elements out of that list and then doing a couple things. In this case, I have to unlist it, and then I have to convert it from a character field to a text, to a date time object. And then I have to just pull out the year piece. So in other words, I'm writing kind of the expressions to transform the results in that nested list to specifically what I need here. So here's an example where I have to subtract 273 because for whatever reason, the CalAdapt data, temperature data comes down as Kelvin. So to convert that to Celsius, make a subtraction. Right. So this is going to be variable, and this often, it takes a little bit of trial and error there, but it does get better. But when we're done with that, and it's really fast, we have a tibble. We are ready to roll with the next step. Okay. Any questions? Okay, let's go into our next notebook. What's the time now? We've been going, let's take a 5-minute break. Okay, so I'm assuming that you have opened up Posit Cloud and opened up the RStudio project that we used last week. So I'm going to go ahead and close all my windows here because I want to start fresh. This is generally good practice. And I'm going to use the broom icon, clean out my console. I'm going to use the broom icon in the environment pane to clean out all the variables in memory. And just for good measure, I'm going to restart my R session. So if you go to the session menu and then restart R, it'll give you a fresh session. So if you are an RStudio desktop power user, you can run this command. I'm putting here in the chat window, and this will download the RStudio project that we are working with to your desktop. And by default, it'll throw it on your desktop. But if you do want to put it somewhere else, you can add the another argument there. So again, if you're working on your laptop in RStudio desktop and you've installed the packages, use one of those commands, run one of those commands I put in the chat window. Okay, but let's go ahead and go into the exercises folder. So in the files pane, go into the exercises folder and open up exercise 2, recent past synoptic. All right. And I'm going to run through this today. I'm going to try visual mode because Shane convinced me this is superior. Let's see.
That scares me, Andy.
Okay, so I am, and you know, and if you're a little bit behind or half of this doesn't make sense to you, feel free to just watch. You'll probably still get something out of this. But in this notebook, we're going to go through what I just covered using the HTTR2 package to develop an API request object for Synoptic, and then we're going to call it. And specifically, we're trying to get daily minimum and maximum temperature. We are going to get the CIMIS station data, right? The same one we worked with last week. And we want to get recent data starting from January 1st through last year. And we want to produce a tibble. What we want to get out of this at the end of the day is going to be a data frame that has a column for the location ID, which in this case, we can just say will be the CIMIS station value, the period, RP, and there's a column here for period because soon, although I don't know if we'll get to it today, soon though, we're going to also get more data for the same location for the next 7 days. And then after that, for the next several months, right? So RP stands for recent past. So eventually we're going to stack these all together. We also want a column for the date, right? So from January 1st up through May 9th. The minimum daily temperature and the maximum daily temperature. We'll call those TASMIN and TASMAX. So that's our goal, right? We're going to call the API and we're going to create a tibble with those columns when we're all done. So let's get started. The first thing to do is to read the documentation. And we'll go through that together here. But as I mentioned, Synoptic has an API service and their niche is republishing weather station data. That's what they do very well. Something else that you'll learn soon, or you could read about, is that they generally provide weather station data hourly. It depends what they get from the provider, right? But CIMIS data is recorded hourly. And you do need a token, right? There is an open access plan. It's fairly generous. Okay, so the very first thing, though, is we need to do our homework. We need to figure out what are the pieces that we're going to require here. Now, you might think this is a lot of excessive detail and you're not really interested in Synoptic. The same process, though, would be helpful for many, many weather APIs. And one of the reasons I decided to go into this level of detail is because there's a lot of weather stations out there. There's a lot of private on-farm processes. A lot of growers are getting grants to put on weather stations. All of the weather station providers are selling a package, which includes a data portal, and they're using their own API to power their website. So there's a lot of these APIs out there. So go ahead and get yourself a token if you haven't already. I'm going to blow through this because I assume you've already done this. All right. But let's go ahead and we have to read about the specifically. This is where we're going to go next. We're going to read the documentation for the time series endpoint of the API. So I'm going to put this in the chat window. I want everybody to go here because we're going to go through this together, right? That doesn't look right. Let's try this again. That's better. Okay, so I put a link in the chat window to the documentation for the time series endpoint. And let's go look in there because this is what we need to read. And this has all the pieces of information that we need to use when we make our API request object. So the first thing we need to grab here is I'm put a little sticky note here because I'm going to take notes as we read through this. All right, so the base URL equals to that. Using my little sticky pad here just to kind of keep track. All right, so that's the URL that we're going to use when we create our request object. Okay, let's talk about the parameters, the query parameters. One parameter we have to pass will be token, right? So that's going to be equal to our token, right? So we have to give them that. Let's keep reading here. Okay, so obviously we want a start and end date. So we need to add a start query parameter, and that should look like, it should look like this. There's a specific format that we have to give it for the past. And another thing that's important to note here is that the start should be in UTC, right? So that's important. If we want midnight on January 1st as the first time, the first date, then what we provide as the value for the start parameter is midnight California time, but converted to UTC, right? Which is like probably 7 or 8 a.m. in London. Likewise, we need an end parameter. All right. Let's keep reading down here. So OB, there's an argument called OB time zone. That looks like it's useful. So we're going to use OB time zone equals local. What that means, again, if you read the documentation, it means when we pass this, it's going to send us back the time values for this location in local time, in California time. So that means we don't have to worry about converting the timestamps to California time when we get it back. Right? Save us a little bit of work. Let them do that for us. Units is another useful parameter. So we're going to say units equal to English, right? This will give us our temperature values in Fahrenheit. You could read a little bit more there. Now we also have to specify the location. I'm going to go, so I scrolled back up here in the documentation, and I'm going to click on this little box here that tells me how to specify the location. So there's a few ways that you can specify the location, right? There's 120,000 weather stations, and we don't want all of them. So the one we're going to use, there's a parameter called STID. So we're going to use that. And then that's going to be equal to every station in the Synoptic API has a unique station ID number. And I believe it's, I've done this a lot, so I think it's CI077 for CIMA station number 77. But I'll show you where you find that out, because maybe you want to find out the weather at, maybe the Caltrans station that's close to your house, right? They've got lots of different networks. So that's all we need for the location. If we wanted to get all the weather stations in a certain state or certain county or that are part of a certain network, you could use some of those other parameters there. Okay, how do you specify multiple stations? I like your thinking there. We would have to read the documentation, but let's say if we knew exactly that we wanted CIMA station 77, CIMA station 75, you can pass as the value a single or comma separated value list of CIMA Labs station IDs, right? So we could add comma and then add some stuff. Or we could not use station ID as the parameter, but we could use some combination of these other options. So we could say, I want all of the CAL FIRE weather stations in Mariposa County. And if there are any there, you'll get them all back. Okay, we're kind of going through this quickly. That's kind of the gist of it. Okay, so what else do we need here? We've got start date, we've got the end date, a couple options. We haven't told it what weather variables we want, right? Because we certainly don't want all of them. So for that, we're going to have to come down and find out what are the variables. And it's not show empty vars. I think it's called vars, but where is that described here? Precip, nope. I think I went past it. Oh, here we go. I just saw it. There we go, vars. Okay, so vars, this is the parameter that we need to pass as part of our API request object that tells what variables we want. And there's a whole list of them here. So I can click on there to see what are the valid variables that we could use. And the one that we're going to use is air temp. Again, we are getting hourly data. So we are going to have to calculate the daily and minimum maximum ourselves, because CIMIS doesn't have an option to get data at a daily time. Okay, so I think that's good enough. So let's go back to Posit Cloud. So now we've read the documentation. We know what is the base URL and what are the key parameters that we need to pass in our API request object. Okay, so code chunk number 1, go ahead and run that. If you're still with me, click in the cell there and run it. And then code chunk number 2, run that. And that's where we are defining a variable for the base URL, which we just discovered in the API documentation. Coming further down, go ahead and run code chunk number 3. This is where we are loading our token. I have a feeling this is a dummy token in that text file, so this may not work. But you could, so if you have a token, if you've created your own public token, go ahead and modify code chunk number 3 and stick it in there, so that you can actually grab it from your other one. Okay, the station code chunk number 4 is the station ID, so we're setting that up as a variable. I didn't say how to find the station IDs. If you go to the Synoptic Data Viewer, I'm going to click this Synoptic Data Viewer. Here's a URL. This is one way that you can get it. They have a data viewer. You may have to be logged in to open it. But you can zoom in here and you'll see it's a web map, right? You can zoom in, and when you hover over a station, so you zoom into the station that you want to get, and the very first thing that you see in the pop-up window is the station ID, and it is case sensitive, right? So we're running out of time, but if you only want to see the CIMIS stations, if you only want to see the stations that had data as of yesterday, you can use the little filter, you can filter the networks, you can filter the dates. I would say specifically for, if you want to find CIMIS stations, because there is a latency, this map is not going to have any CIMIS stations that show data as of 1 minute ago. So the first thing you want to do is, if you are using the Synoptic Data Viewer to find the station ID, click on there, move it to historic mode, and then say, let's find the, show me the data from yesterday. All right. So, and then I could maybe then do under network selection, click on custom, search for CIMIS. There it is, select it, come down and apply. And now it'll just show me the CIMIS stations that had data as of yesterday. Right? So we can see all of those. You can explore the other station networks, but again, you click on one of them and you can see in the top of pop-up window, you can see the name of that station. And then if you click on it, you'll see the recent data, and so on and so forth. Okay, so I'm back in the RStudio project in Posit Cloud. Code chunk number 4, we've entered the name of this station that we're going to query here from Oakville. It's CI077. And then code chunk number 5, go ahead and run that. And what we're doing here is we are creating the date time object when we want to start from, which is January 1st, midnight, right? Because that's what our model tells us to do. Right now, we've created as a date time object, a posit CT object, but what we need to give to the API is a character object. So code chunk number 6 is taking that date time object, typing it into with TZ to convert it to UTC time, because that's something else the documentation told us to do, and then piping that into the format function to put it in that format that, again, that the API expects as a character object. So that's what code chunk number 6 is doing. And we're just saving these pieces as variables. And then in a second here, we'll put them all together in an API request object. Code chunk number 7, click on that and run the whole thing. We're doing the exact same thing. And getting the date time for 11 p.m. yesterday. Because again, we're trying to create daily degree days. And the last day that we could get a full day of record from with is yesterday. So that's what code chunk number 7 is. Code chunk number 8 is then converting that to its text representation. And then finally, code chunk number 9, we run that. We are creating a variable called weather vars. Right? So at this point, we have created variables, everything that we need to pass to the API. The base URL, the start and end date, and the special formats, the weather variables we want, the name of the station, we're ready to go. So come down to code chunk number 10 and run that. And, oh, weather vars, did I not run that? Let's try that again. Why is it not running weather vars? Oh, unexpected symbol. Power work. Got a syntax error somewhere. Let me try this. I want everything above it.
Oh, you're gonna, okay.
All right, I'm gonna run that in the console, see if this works. Okay, I didn't see any other error messages, so I'm gonna just run that in the console. Okay, let's try again. So code chunk number 10 is where we're going to create our API request object. Okay, now that worked. And you can actually see code chunk number 10. You can see all of the pieces of the API request object. You can see how we're putting them together. We're using those functions from HTTR. We're mixing and matching. We're putting in the headers. We're putting in the request parameters. And then finally, we can call the API. We've created our request object. Code chunk number 11, we'll do a dry run and save it to, it's not printing out the results. Oh, let me close this up. And then code chunk number 12 is where we actually call the API. So if you run code chunk number 12, what it's written to actually save a copy of the request that we ran last week. But if you did actually enter your own valid synoptic token further up, then you can uncomment the 2 lines that are commented out and actually make the request go live. All right. Okay, now, see, this is why I don't like previewing, because these things are not appearing below it. Okay, other folks are having issues. I'm going to go back to source mode. Make sure what the issues are. I'm going to run all this above. This one here, it's working. Yeah, I'll have to debug. This is a Cordo Markdown issue. Okay, so I ran it in the source editing mode and didn't have any problems. Okay, code chunk. Let's quickly finish up here. So code chunk number 13, we are looking at the response that we got back. Again, feeding the response object that we saved and piping it into the response status function. That's code chunk number 13. We'll skip the challenge, but if you wanted to get the data in Celsius and not Fahrenheit, how would you modify your API request object? Code chunk number 15 now we have the challenge of, we have this response, and it's got data in it, we've got to get the data out. So the first thing we'll do in code check number 15 is take the body and put it into JSON, or run it through a JSON filter, and now we have a list. And in code check number 16, it's giving us a really, really good suggestion to view the structure of this list, because we don't know what it contains, in a view window. So I'm going to manually select that and then run it so that I open up this list in a view pane. So the view function, which we've seen before working with data frames, also is a really good way to look at a list structure, particularly lists that you get back from APIs, which can be quite nested. And you can just kind of see, okay, so what we get back, it's a list of 4 elements. The first one doesn't look very useful. It's information about the station. We know what the station was. The second element is called summary, also not terribly useful, kind of tells us about the data. The next one might be useful. QC summary, quality control. No, that's not very useful. And then finally we have units. Okay, so I missed the data here somewhere. I think it's under station. Yeah, so under the station, the first element, if you drill down, you can actually see where the data are, right? So under observations, so this is, I won't go into detail, but this is where you would have to like drill into your list structure to figure out how to turn, how to pull out the dates, how to pull out the temperature values so that you can throw them into a data frame. And that's what we're doing in code chunks number 18. I'm going to run through these quickly and then we'll stop. Code chunk number 19, code chunk number 20. So basically what we're doing in these code chunks is we're pulling out specific pieces of the results. And then lastly, code chunk number 21 is pulling out the temperature values. And finally, code chunk number 22 and code chunk number 23 puts them all together. Right? So I'm going to stop there. Once again, dramatically underestimated the amount of time it would take to get through all this. But we went through a pretty detailed, a pretty thorough workflow of calling an API, querying it, and using it. So I would say your homework for next week or for 2 weeks from now is to do something like this, get data from a weather station near your house, near your workplace, or an area that you're interested in. Okay, and then we'll pick up next time where we left off. And you can read through the rest of these code chunks here. A lot of this is just caching. Okay, so thank you, everybody. And I will stay on if you'd like to chat some more. Otherwise, we will pick up next time and do something a little bit easier, because this was hard, right? We had to like we had to roll our own wrapper. But next time for the 7-day forecast and the seasonal forecast, we'll actually use our packages.